Okay, you all probably have heard the big news this week coming out of the US. It was about ignition that the National Ignition Facility accomplished for nuclear fusion. Why is it a big news? Basically, uh, when fusion happens, you have uh, the fusing of two elements that are going to produce a third element in the process, release some energy, so that additional energy can then become a self-sustained nuclear fusion process which can produce literally infinite energy like the stars or the sun produce. Obviously sun is going to burn up someday by using all the fuel, so when we say infinite there is of course a limit. So what is the sun doing? Taking hydrogen atoms and combining them, or hydrogen molecule, and combining them and producing helium. So that helium is heavier than hydrogen, so the nuclear fusion itself is producing huge amounts of energy and temperatures which make the gases and the core expand, whereas the increased gravity tends to pull it in because of the formation of helium. This gravitational pull actually tends to be happens to be very important because that keeps the plasma. So at these very high temperatures you are dealing with millions of degrees centigrade or Kelvin, which means the plasma can just fly away and diffuse away its energy, but the gravity puts it into a higher density where it remains stable, and then the self-sustained nuclear furnace in the sun's core can go on. Of course, sun has been expanding over the time of its life from 4.6 billion years ago, 30% less luminous when it started, which we looked at as the faint young sun paradox, about how water could have remained in liquid form when the sun was 30% less luminous. Now sun has been expanding for this long, and in about 100 million years the energy coming to the earth because of the sun's expansion and increasing luminosity will become so high that all the water will get vaporized. But that's a separate issue. Coming back to ignition, the US National Ignition Facility, where the target chamber exists as shown here, is the size of 3 American football fields. So you can imagine how big that is. And basically NIF has used the method of focusing 192 laser beams onto a target the size of a pencil eraser to initiate fusion. This figure is from an article from 2021 when the first successful ignition was accomplished, but it turned out that this shot or the experiment could not be replicated, so they have redone it by redesigning the experiments, increasing the power of the lasers and so on. Essentially they put frozen deuterium and tritium into a little pea-sized gold cylinder and then blasted it with these lasers to create temperatures of the order of 3 million degrees, which caused the fusion to happen. Deuterium and tritium together produced helium, and then some cascading reactions happened. The cylinder collapsed. They had put in about 2.05 megajoules of energy, and the fusion reaction produced 3.13, so 50% more energy than they had put in, which is a big deal. This is not accounting for the energy used to produce the lasers, but that's not the point. The point is, given the energy for ignition, can there be additional energy production so that the nuclear fusion reactions can continue? So it's a huge step. Somebody commented that this is like the first flight of the Wright brothers. So if you think about the progress we made since then in air travel and space travel, it's been pretty amazing. Of course, now for fusion we need to move much faster to get decarbonization and carbon-free energy through, let's say, fusion, to meet our decarbonization net zero goals and to meet our global warming targets of 2 degrees C or 1.5 degrees C with 67% probability by 2100. What remains, of course, the ignition was successful, but in a real reactor that has to serve electricity into a grid or some other like a small reactor which would be supplying energy to a particular function, particular industry, manufacturing process or whatever, that has to do this process multiple times a second. So the recycling after such heating and the heating of the lasers itself occurs is not trivial. So those considerations were not taken into account in this experiment. This was just a demonstration of ignition, and it has been successfully achieved. There are other details that are not directly related to ignition but generally related to having sustained fusion reactors, and how the ignition is done actually doesn't matter. So there are many ways in which ignitions are being tried. This is one method that's now shown to be replicable and successful. So let's look at some of the other issues that have to be dealt with before we get to utility scale or small reactor scale fusion going to have sustained energy supplies. This is just a schematic showing how the most straightforward and lowest energy version of the proton-proton chain producing helium-4 can happen. Why do we use deuterium and tritium? Because they can be fused at low temperatures and produce lower temperature plasma, but we'll see in a minute that they also produce most of the energy as neutrons. So it's not electricity, so you need electrons, charged particles. So in this case the energy of the neutrons has to be harnessed by basically containing the blast of neutrons with a container that's going to convert the neutron energy into heat, and that heat has to be used to boil water and drive turbine with steam and such. Of course, the constant bombardment of neutron and the energy creates radioactivity from the container itself, so we have to worry about that. So basically you have H and H combining to form deuterium and hydrogen, releasing some energy, and then they combine to form tritium and some energy. Then you have another chain of reactions coming along with another tritium, so you have two tritiums colliding to produce 2H atoms and helium. So you have protons bouncing around, and their position is shown here with this gray positron is position. Positrons are shown here with the gray circles, and protons are shown with the red circles, and neutrons are shown with the gray circles. Okay, so this is how the reactions work, but there are other fuels that can be used for getting over some of the issues of deuterium tritium. So many reactors fuse deuterium with tritium to release energy. This mix ignites and or creates a self-sustaining fusion reaction at around 100 million Kelvin. It produces neutrons which can make the chamber radioactive. So you have deuterium and tritium producing helium, and then neutrons, which we just talked about. Other reactions such as fusing protons with boron 11b don't produce neutrons, but ignition requires higher temperatures. So in this case you have proton and boron 11 combining to produce boron 11 and 3 alpha particles here, which are basically plasma, which is going to give you all the energy. But then controlling the plasma becomes a massive task, because as we said, it's very high temperature ionized gases that are going to be just diffusing away and losing their energy unless you can contain them and then convert that plasma into energy. So there are many approaches used. This is another article from Nature from 2021. Look at the tokamak. So ITER and other facilities are using this. Superconducting magnetic coils cooled by liquid helium hold plasma in a toroidal vessel. So there's the magnetic coils. Turns out that cooling with liquid helium is a very difficult task, because helium tends to leak out of the smallest possible gaps in the system and so on, whereas if you use magnets made of high temperature superconductors instead of the normal superconducting magnetic coils, then they can produce stronger fields and can be cooled more easily with liquid nitrogen, which is quite abundant and doesn't have this problem of liquid helium leaking out everywhere. This allows more compact spherical tokamaks to be built, as you can see here. This is called the mini tokamak. So Tokamak Energy, Commonwealth Fusion Systems and others are using this approach, whereas you have linear colliding beam reactor, which is being used by TAE. I think this is a Chinese firm, but you can check it out. Packets of plasma are fired into a central chamber and rotate rapidly inside a solenoid. That's a coiled wire electromagnet. So you have plasma being produced into the and being bombarded into the central chamber, and you have fuel beams there coming in that interact with the plasma and produce the energy you want. Obviously, I am not giving you a whole lot of details, but just trying to point out how we are going to advance from the excitement of ignition that has been reported to actually accomplishing functional fusion reactors. So the article talks about how enormous amount of funding is being pumped, and large number of private companies have been set up to work on fusion and work on these problems of controlling plasma and accomplishing fusion energy harnessing. So Fusion Rush, firms and governments are developing many kinds of fusion reactors. They all heat gas to create a plasma confined at such high temperatures that atomic nuclei fuse, releasing energy that can be harnessed for electricity. Here are 5 prominent designs. Magnetized target reactor used by Generalized Fusion of UK. A spinning ball of liquid metal confines plasma. Pistons then rapidly compress it. The plasma is allowed to expand and then compressed again. So here are the pistons, here is the liquid metal, and here is the ball that will create this plasma that's going to be providing the fusion. Stellarator is used by Wendelstein 7X. A complicated twisted loop of magnetic fields confines the plasma. So it's all about confining the plasma to allow stable fusion, sustained reactions to occur. Fusion funding. Private fusion firms, sorry, I think I have misplaced, no, it's okay. Fusion funding. So private fusion firms have disclosed more than 2.4 billion in funding. TAE Technologies has $880 million. Helion Energy 578. Commonwealth Fusion Systems 250. General Fusion 200. Tokamak Energy 200, and other firms 302, adding up to 2.4 billion in funding. Of course, a functional reactor is going to cost much more. So the cost of just implementing the systems is not small, but it's big business, big science, and eventually if it works, then it's going to be big money as well. The future promises. Private firms are making bold promises about delivering commercial fusion reactors in the 2030s. So there is the private and state-sponsored efforts. So by this is what we are looking at till 2020. By 2025, we are going to have giant international effort at ITER and Helion net electricity, small amounts from the Polaris reactors. We're going to have test runs, state-sponsored and private efforts. Commonwealth Fusion Systems, first fusion machine expected to generate more energy than it uses by the 2030 timescale. General Fusion, Operate UK demonstration plant is expected. TAE Technologies, reactors ready for commercialization are expected by late 2020s. By the 2035 horizon, CFS aims to have 200 megawatt plant supplying electricity grid in early 2030s. So that's really going to utility scale and supplying the grid. General Fusion targets reactors for sale in early 2030s. First Light Fusion anticipates its first power plant in the 2030s. First power plant, okay, fusion power plant. Tokamak Energy, fusion power plant pilot in 2030s and heading to 2040. ITER to run fusion with deuterium tritium fuel. China Fusion engineering test reactor might complete construction in 2030s, and UK Atomic Energy Authority hopes Step Fusion power plant can supply energy to national grid. So obviously these are exciting times for nuclear fusion, and they cannot come too soon because we are already going along with these emissions that are not bending the curve at all in terms of turning down the total CO2 that is being emitted each year. COVID slowed it down, we recovered, and now we are going fast again, but that's not good for the net zero and the decarbonization goals. But nuclear fusion itself is now being touted as something that can really take care of the energy issue for dealing with decarbonization and to meet our global warming targets of 2 degrees C or even 1.5 degrees C by 2100 with 67% probability. But there are many people who will tell you we shouldn't be so optimistic about the nuclear fusion being the holy grail or the silver bullet. Nonetheless, we looked at the issues. Ignition is good news. A lot of investments by private and state entities into even commercial players in the fusion research is very good. And if we use COVID as an example, then throwing so many resources at the vaccine process did produce some success in terms of vaccines that ended up working mostly as expected, even though it'll be a while before we figure out exactly whether they produced any kind of long-lasting side effects and so on. Nonetheless, nuclear fusion again is something that needs to work, and any news is good news at this point. So just keep the obstacles along the way we still have to get over, but keep tracking the good news. And again, remember that I'm not a physicist, so I'm just doing this as an introduction based on my own research just to give you a sense of where things are. So if you want the details, you need to read up on your own. Okay.